We now learn about U-substitution, which is one of the techniques used when using the method of substitution for integration. Now we're going to do this with some examples. Let's go right ahead. Say we have to find the integral of 2x times cosine of x squared minus 4. Now, looking at this integral, the first thing I want to draw your attention towards is that we're trying to integrate a product of two functions. Indeed, we have 2x, which is multiplying the composite function cosine of x squared minus 4. Now, as soon as we have a composite function inside the product, the first thing we want to do is look at the function inside the composite function. In this case, that would be x squared minus 4. And we compare that to the other function in the product. That would be 2x. Comparing these two functions, it doesn't take us too long to see that 2x is the derivative of x squared minus 4. That means that if I were to call x squared minus 4 u, then 2x would be du dx. And this is the scenario which tells us to use U-substitution. So I'm going to go ahead and solve this or find this integral with U-substitution in 4 steps. As a first step, step 1, I'll define a new variable, which I'll call u. I'll say let u equal to x squared minus 4. Notice that the new variable u is nothing more than the function inside the composite function. I now look at the derivative, du dx, which equals to 2x. And rearranging this allows me to write the differential of u. That's du, which equals to 2x times dx. And that's my first step done. I now move on to step 2, in which I will rewrite this integral in terms of this new variable u. That's the integral of 2x times cosine of x squared minus 4 equals to the integral of, well, let's see. We have 2x times dx in our original integral, and we've just seen that that's equal to du. Furthermore, I have cosine of x squared minus 4, and we've just defined x squared minus 4 as u. So when I rewrite this integral, it turns into the integral of cosine of u, du. Now we've written this integral in terms of our new variable u. Indeed, we can't see any x's here, so we have an integral in terms of u. And we can now move on to step 3. Our third step is to integrate cosine of u with respect to u. And the way we do this is quite simple. I treat u as I would any other variable. We know that if we integrate cosine of x, we'll get sine of x. This is no different. The integral of cosine of u is equal to sine of u, plus some constant of integration, c. I now move on to the fourth and final step, in which I rewrite this result I found at the end of step 3 in terms of x. And to do that, I just go back to step 1, in which I defined u as x squared minus 4. So let's go ahead and do that. We now state that sine of u plus c is equal to sine of x squared minus 4 plus c. And that's it. We've just integrated this using U-substitution. Now let's see in a bit more detail how U-substitution actually works. And I'll just write this on the right-hand side here. U-substitution. This scenario, which tells us to use U-substitution, is always going to look something like this. The integral of du dx times f of u of x. In other words, the scenario is we're given a product of two functions, one of which is a composite function. The other function is nothing more than the derivative or some scalar multiple of the derivative of the function inside the composite function. Now we'll often just write this as the integral of du dx times f of u. And that really sort of highlights the fact that u is treated as a variable rather than a function. And the way this works out is that these dx's kind of cancel each other out. And then we're left with the integral of du times f of u. And that can be rewritten as the integral of f of u du. Then we simply integrate f of u in exactly the same way that we would integrate f of x. And that would lead to the antiderivative, capital F. So we would find capital F of u plus some constant of integration c. And finally, we would write u back in terms of x. So this equals to capital F of u of x plus c. And that's how U-substitution really works. So let's go right ahead and look at another example. Let's say we need to find the integral of 6x squared times sine of x cubed plus 5. Well, again, the first thing we notice here is that we're trying to integrate a product of two functions. We have 6x squared, which is multiplying a composite function sine of x cubed plus 5. So our reflex is to look at the function inside the composite function, that's x cubed plus 5, and to compare it to the other function in the product. So that's 6x squared. Now, looking at these two, it doesn't take us too long to see that if we were to differentiate x cubed plus 5, we'd get 3x squared, but we have 6x squared. So that's 2 times the derivative. What I'm saying here is, if I let x cubed plus 5 equal to u, then 6x squared would be 2 times du dx. So this is a scenario for u substitution. So let's go ahead and solve this with our 4 steps. Step 1, we're going to define the new variable, so let u equal to x cubed plus 5. Then its derivative, du dx, will equal to 3x squared. And the differential du would therefore be du equals to 3x squared dx. Now, in our integral, we don't have 3x squared dx, we have 6x squared multiplying dx. And that's just 2 times du. So we can go ahead and actually write that and state that 6x squared dx equals to 2 du. Okay, that's our first step done. We move on to the second step, step 2, in which we rewrite this integral in terms of the new variable u. That would be the integral of 6x squared times sine of x cubed plus 5 equals to the integral of, let's see, we have 6x squared multiplying dx, and as we've just seen, that's 2 times du. And we also have sine of x cubed plus 5. But x cubed plus 5 we defined as u. So this will turn into the integral of sine of u times 2 du, which we can write as 2 times the integral of sine of u. And we're done. We move on to our third step, and the third step is to integrate this with respect to u. And that would be 2 times the integral of sine of u equals to, well, the integral of sine is negative cosine, so this will turn into negative 2 times cosine of u plus some constant of integration, c. We're done. We move on to our fourth and final step, step 4, in which we rewrite this answer we found in step 3 in terms of x. And to do that, we simply replace u by its expression, which is x cubed plus 5. So let's go ahead and do that. We can state that negative 2 times cosine of u plus c equals to negative 2 times cosine of x cubed plus 5 plus c. And that's the final answer. We've just found this integral using U-substitution. Okay, we're going to move on to the next video in which we're going to solve a couple more examples of using U-substitution for integration. But for now, what you want to make sure you take away with you from this tutorial is the following. We use U-substitution as soon as we're faced with an integral that can be written like this. The integral of du dx times f of u of x. In other words, we use U-substitution as soon as we have to integrate a product of two functions, one of which is a composite function, and the other is the derivative of the function inside the composite function. Now, at times, we'll be given functions in which we don't have exactly du dx. We'll often just have something like alpha du dx, where alpha is just some real number like 2 or 1/5 or 1/10 or 50. But so long as we have something looking like this, then we're all set to use U-substitution. Okay, everyone, I really hope this helped. And if it did, please hit like on this video and even subscribe to our channel. It really does help us. I'll see you soon.